So recently, I had a gas compressor that was just randomly dropping its discharge pressure. And I mean, randomly. Like you could stand in front of the compressor and watch it run, and everything looked fine. All the gauges were green, pressures were good, compressor was loaded, no alarms, nothing. And then all of a sudden, the discharge pressure just falls off and everything starts hunting. The skid starts fighting itself, and then after a few minutes, it recovered. Like nothing happened at all. And you really couldn't see this problem standing in front of the machine because the thing is when you were staring at the machine, all the data that you were getting was within expectations. So it was like a something that was happening over a longer period of time. So just that snapshot of data that you were looking at really wasn't getting what you needed to. So the only place that this problem really existed was in the data. And once we started pulling the data and really started digging through it, there it was. It was clear as day. It was failing on a pretty consistent cycle. So it was like every 10 to 15 minutes, like clockwork. So today, what I want to talk about is industrial data and how we collect it, what it can actually do for you, and the trap that I see all the time where people collect this mountain of data and do absolutely nothing with it. Welcome to From the Bucket, where controls design meets reality. I'm your host, Keely Smith. In this podcast, we explore industrial control systems as they exist in the field, not just how they were designed in CAD or how they look on paper, but how they operated in a production environment, how operators and maintenance interfaced with them, and the fun and interesting stories that I've made throughout the years of being a controls engineer. So, before we get into it, this episode is going to be a little bit different. So, the last several episodes, we've been walking through my career chronologically, and we're going to keep doing that. But right now, over the last few months of work outside of this podcast, I've been doing a ton of data analysis. And honestly, it's been one of the more interesting parts of my year. So I wanted to take a detour and kind of talk about it while it's fresh. If you're here for the career stories, don't worry, we'll pick that up in the next episode. So with that, let's kind of dig into this world of data. So here's something that I don't think that people outside this world realize is that industrial data collection is a massive spectrum. So on one end, you've got the guy with the clipboard. And I'm not joking about this. There are facilities running right now where their data collection is an operator walking around a floor every hour, half hour with a paper form. And they write down all of their different process conditions. So their pressures, temperatures, levels, and they fill out their form and they hand it in at the end of the shift. And at a level, I mean, that's data collection. That's a data program that this facility has. Then you've got kind of in the middle of the spectrum where you've got data collection happening inside the PLC. And because and the PLC is already seeing everything. So you store some of your values there. Maybe you buffer some of your trends, keep a little bit of history. It's better than paper, but it's still kind of limited. You're only keeping what you thought to keep, and usually it's not very much of it. I mean, the thing with the PLCs is that they're really not made to be storing massive amounts of data on them. So you get a pretty small window, and a lot of times you end up rolling that data out. So if, for example, you're trying to capture the last day of running, well, when you get to the next day of running, you're going to start dropping off that data at the back end of it. So you end up losing data. So yeah, sure, you got this window, but it's not very big of a window. And then on the far end of the spectrum, you've got the full setup, the SCADA, the historians, the whole deal. Every point logged, timestamped, trended, going back months or even years. And the kind of system where you can ask a question about what happened 3 weeks ago, Tuesday at 2 a.m., and actually get an answer. And here's the thing that I want to be really clear about. Every level of this spectrum is valid. I work with customers across all of these different spectrums. Some of them are the clipboard customers, and they're always going to be the clipboard customers, and that's fine. It's a business decision, and for their operation, it might genuinely be the right one. But what level you're at changes what's possible. And that's really what this episode's about, is talking about kind of what it is that you can do with this data that is living inside of your facility. And I think one of the things that really fascinates me about this industrial data is how much it really changes depending on your industry. So, my time of working in food and beverage, we did care about data, but what we really cared about was the line data, the uptime, the throughput, OEE. How many cartons did we make that day? How many of them actually made it to the end of the line? Where did we lose time? Which machines were the bottlenecks? All of that stuff, right? And don't get me wrong, that data is incredibly important. OEE matters no matter what industry you're in. So I'm not knocking it. It's just it's kind of funny to me looking at it now after working in some different industries of like how limited that scope was of what we were trying to do with the data. But here's the difference. That kind of data gets you into a general area. It tells you that, hey, something at the end of your line is your problem child. Sometimes it can even point you to a specific piece of machinery. So maybe your palletizer is the bottleneck of your line. And it tells you things like, hey, line 3 ran worse on second shift than it did and over first shift. So, it points at a part of the processor or process. And the thing is that again, that data that's great. I mean, it's operational data that you can create business decisions on. And then I moved into process controls and started working with gas compressors. And the whole purpose of the data changed. See, because the thing with compressors is the data is not really about the throughput. A lot of times you're looking at the data for health. You're watching your vibrations, your temperatures, your pressures, your differential pressures across filters. You're looking at the things that could give you that early warning of something going wrong. A bearing starting to fail, something running too hot, a filter loading up over time. And it's kind of fascinating, right? Because when you look at the contrasts that I've had in my career between food and beverage and really caring about that throughput to a piece of machinery that's running 24/7 for 6 months at a time, what you're looking at on the data is it's radically different. And I think that with looking at that equipment health, the resolution is completely different. This data doesn't just get you to a general area, it narrows you down to a specific component, sometimes a specific failure mode on a specific component. It's the same umbrella of industrial automation, but it's radically different questions that you have to ask yourself of what this data is that you're looking at and what you're trying to get out of it. So let's go back to the compressor from the cold open on this episode. So skid's randomly losing discharge pressure. When you're standing in front of it, you can't really see what's wrong. So, we started pulling the data. And the first thing that the data showed was the cycle. So every 10 to 15 minutes, the discharge pressure falls off. And that right there changed everything, because now we're not looking at something random. We're looking at something that's happening on a cycle. So, because the thing is that random is hard. No matter what industry you're in, if you have something that is truly happening at random, that's a lot harder to determine. Anytime that you look at data and you see a cycle, it's a clue. So now we start looking at, what else is moving on that same cycle, and there it was. So we found that a pressure regulation valve was starting to move during that cycle, because we were getting a feedback signal from that valve, and over the course of those 10 to 15 minutes, you can slowly watch it creep open, just a little bit at a time, so slow enough that when you're standing there staring at the data, again, nothing really truly looks off, because it's moving slowly enough that you're not seeing the big changes. And the other part of this is that as that valve is slowly creeping open, the rest of the process conditions are modifying themselves to catch it. So if all you're looking at is kind of that skid discharge pressure, it looked fine, because the rest of the control system was doing what it needed to keep that pressure to where it was. So it opens and it opens and it opens until it got to a point where it opened far enough that the skid's discharge pressure started dropping off. And part of what was happening was it got past the point where the slight modifications that the control system was doing couldn't make a slight correction anymore. And that's when all of a sudden you start getting all this violent movement on the data, because the second that pressure falls, the valve starts to slam shut, because now all of a sudden the valve's like, wait a second, we're losing pressure. We need to close up fast because we're going to lose the compressor load. So that spikes the discharge pressure right back up. At the same time, the capacity control of the compressor sees that pressure drop and also tries to load that compressor up. So now you've got two controls responses fighting each other, and they start hunting. So your discharge pressure starts to swing back and forth. Everything else is chasing everything else until finally it settles, and then it's like it never happened. Then that valve slowly starts to creep again over time. 10, 15 minutes later, the same show. And here's the part that I love. Going through the data, you don't just find one problem. So we ended up finding two problems. The valve itself was failing, and there was also a slow air bleed happening on top of it. So we had two separate issues, both kind of hiding in that same data set. And, both were kind of invisible when you're staring at the machine. So that data was kind of that piece that we were really missing, that was able to get us to right where we needed to be. And now here's really the question that's worth asking. What does this look like without data? Because we haven't always collected data on some of this equipment, right? So uh, a lot of the older pieces of equipment that I work on, they don't have this data collection. And without that data, you just start replacing components. You go off of what you've seen in the past, what the symptoms that you are seeing, do they match up with something that you've seen before? Is it something that looks close? You take your best guess. It's a swag, a scientific wild ass guess. And look, sometimes that swag lands, right? Sometimes you arrive at the exact same conclusion that the data would have given you. That the experience is real, the pattern matching is real. But here's the thing about field problems. Even when it's the same issue you've seen before, it never really truly looks exactly the same. So you're kind of matching fuzzy patterns against fuzzy memories. And, every wrong guess is a part ordered, another deployment where somebody has to go out and replace a part. So now you've got multiple different groups coming out to a site. So if we're replacing a mechanical component, we've got to get mechanics out here. We've got to isolate the skid. We've got to go do all these things to replace that component, all with the hopes that, hey, after we do that, we're going to start it up and it's going to work. So, there's a lot to be said about the kind of that field experience, but, you know, this is not to say that the data never replaces that experience. It just kind of really aims it, because what you're doing now with the data is, you're creating a really or you're really pinpointing that problem, and now you have an idea of how to fix it, because now you're really laser focused on, what you think the problem actually is. So at this point, you might be wondering, all right, so how do you actually get this data? What does your system physically look like? So the heart of our data collection is an industrial PC, and it lives there right on the skid. I'm using an OnLogic fanless PC. The fanless matters because all these things sit in an environment that would eat a normal computer alive. No fans means nothing's getting pulled through it. No dust, debris, moving parts to fail. It just kind of sits there and runs around the clock in conditions like that. Like I said, a normal computer wouldn't last in. Because one of the big things when you're doing this data collection is that you need the data collection to be running. It doesn't really help you if you've got unreliable hardware that you're losing hours, days, months of time because something happens. There's a whatever failure you have on the PC. That the PC needs to get turned on and just run. So on that box, I'm running a software package from Open Automation Software to do the data collection. So it's pulling the data off the PLC and logging it into a database. So point by point, time stamped. It's continuously running, and it's just pulling this massive amount of data off of the PLC. So the part that's probably a little less obvious is that I don't actually run this analysis on site. What I do is remote into that on-site server, copy the database down to a local server, and then run the full analysis locally. And part of the reason for this is that you kind of have it's a twofold approach, right? So I create a new copy of that database. So now there's an offline backup of all the data up to that point. And then the other is that now we're running an analysis off of an offline version. So if for whatever reason something happened and the database got corrupted or whatever, we still have the actual live data that we can pull. So cool. I have the data now. So now I can sit there, process it, and chew on it, and out the other end comes a report. And that report, that's the actual product, because collecting the data is never really the it's not the goal. The goal is knowing what the data is telling you. So that report is where that data turns into, something that the customer can act on. I think one thing that's important to kind of note here is that there are hundreds of thousands of different ways to do data collection. So I'm not going to sit here and say, like, oh yeah, look at the way that I'm doing it is great. Um, the way that I'm doing it works very well for what I'm doing and how I'm doing it. Everybody's got their own different way of doing it. Like I said, this is just, the way that we do it. I think that, this is a good kind of segue into, you know, watching the slow stuff happen. So, the first story was it was really an acute problem, something actively failing right now, and the data helped us kind of catch it in the act. But there's a whole nother category of problems that we're looking for that you really can't catch in the act, because they're not acts, they're trends. And this has been one of the biggest pushes for us this year is, this long-term condition monitoring on these skids. So we pull data off these skids on a monthly basis, run the analysis, generate the report, and that report isn't really a snapshot. It's a month of runtime. So every start, every steady state period, it's all laid out so we can look at how things are moving over time. So let me give you an example, because I just ran one of these. So about a month of data, the skid was running maybe half of that window, a dozen starts, and buried in all of that, the report flags a non-drive end bearing temperature that's trending up. Roughly 3 degrees a week across the 8 different runs. Now, 3 degrees a week doesn't really sound like much, and on any single day, it isn't. So the thing is that if you look at a snapshot of data, and if you look at like general alarming on realistically any equipment, there's set points. So if I say that my machine, uh, I've got a temperature sensor that I don't want to exceed 100 degrees, that's pretty obvious, right? If I exceed 100 degrees, I have a problem. What what you don't see on that is if that machine's been running for a month and I started at 80 degrees, and then the next week I'm at 85 degrees, then the next week I'm at 90 degrees, then the next week I'm at 95 degrees. You don't see that because at a machine level, you're still below that threshold. So there's nothing really to talk about at that point. No matter how many times you go back to that piece of equipment, you're going to look at it and say, okay, well, we're still within our operating parameters. We don't have alarms. We don't have any of that stuff. Now you look at it from a data analysis standpoint, and now all of a sudden I have something happening, right? So even though I'm not at a fault level, I can see that things are trending up. I think it's probably important to talk a little bit about some of like this data analysis. And when I talk trends, um, it makes a lot of sense when you think of basically a line graph where uh, you just see the line continuously going up, right? That's part is pretty straightforward. The thing is that there's still a bit of randomness to your data. Like you're never going to get something that just consistently stays pegged on a trend. You're looking for kind of that overall uh, almost a scatter plot of you see the data roughly going up, because the thing is that there are process conditions where that same temperature reading could go down, it could go way up. So realistically, you're kind of looking at the way to do some sort of trending line and come up with a level of confidence. So the bearing trend that I was looking at, I had really high confidence of, how the data just generally kind of lined up. It was a real signal. The phase windings had basically no confidence. The numbers were going up on average, but it was so scattered that the trend was basically meaningless. There's it's noise. So like that data ended up being pretty useless, because we come to find out that we actually had one of our temperature sensors was failing, and because that temperature sensor was failing, it was throwing all of that data all over the place. So the phase trends, they ended up, they kind of looked real. I mean, uh, they were ultimately trending upward, but it just didn't. The data was pretty. I had pretty low confidence in the way that the data was looking. Right. So I've got two findings that look almost identical on the surface. They're both climbing, both about 3 degrees a week, and the one of them is developing a real problem, and the other was just kind of garbage. Now, obviously, with this example, we found that we did have some issues with the temperature transmitter on the phases, but so we were able to actually end up finding two different pieces here. And the thing is that again, this is all of like when you're looking at this data, if you just react to every flag that you end up seeing, you're back to chasing the ghost. The skill is really being able to take that data and, again, figure out what's real and what's not right. And I think one of the really cool things about this data was that you started looking at some different pieces of data, and it started to corroborate itself, because right around that same window that the bearing temperature was climbing, there was also some data that caught some different vibration spikes, basically in that same time period, and they were above the standard threshold, but again, they were still below that alarm threshold. So, from an operator's perspective, there was nothing wrong, and these were pretty high confidence data points. So it wasn't just noise. So now I've got these two different signals that are kind of pointing to the same place. So the bearing temperature is creeping up, and the vibration spiking, and that was really the data starting to tell the story that I needed to know. Something mechanical was developing on that compressor. And here's the payoff for catching it this way. Right now, that's a line item in a report and a planned conversation about how to get ahead of it. Nobody's down, nothing's destroyed, and we have that time to actually plan the outage versus letting the that outage plan it for us. If I'd never been pulling that data, that bearing wouldn't give us a nice warning of, hey, something's starting to go wrong here. We need to start looking into this. It it would just fail. And the thing is that uh, on this particular piece of equipment, that bearing failing would be a huge failure. And so it's really cool being able to look at this and say, hey, you know what? this is what we're seeing, this is what we need to do, and actually taking the time to plan that maintenance event. Um, that's to me, that's the whole value in trending. It turns that 2 a.m. disaster, because let's be honest, when things fail, it's always at 2 a.m. Uh, and we just turn it into a planned outage. And again, like for me, that's something that is just super cool. You're taking all of these random data points. You've got a screen full of data, and being able to take that, look at that, and come up with an actual story of like what's going on with this piece of equipment. Uh, to me, it's really cool because you're creating something out of essentially nothing. And I think probably one of the bigger reasons why I think this is so cool is just because, you know, I've been that controls guy that is getting the call at 2 o'clock in the morning that something's gone down and, hey, need you to come take a look at this and figure out what we need to do to get back up and running. So I think there's probably a little bit of this selfishness here of why I'm so fascinated by what you can do with this industrial data, but you know what? That's okay. The last story that I have is it's definitely my favorite because it kind of flips the whole conversation around. The first two stories are about using data to find problems. And this last one is kind of about using the data to prove that there isn't a problem. So, something that we started to do recently after performing a service is we start to capture that data from the startup. And we're grabbing it fast, high resolution data through that first, uh, I'll call it hour of startup. So in that window, we get to see that 5-10 minutes of startup slash stabilization. Then you get to see the longer term stabilization where, okay, everything's starting to warm up and everything's running well, and you see the equipment kind of operating more or less how it should be. And it's amazing how much those first 15 minutes tell you. You see exactly how the system starts, how it stabilizes, whether your PID loops need tuning. Basically, the whole personality of the equipment shows up in that window. And we actually did this uh, just last week. We bring up the equipment after service, and the data showed a crazy high differential pressure across our filters. And that's the when I say differential pressure, we're talking about the pressure drop across the filters, the final filters, oil filters. And on a snapshot, that's the kind of number that makes a customer nervous, because super high DP on across your filters means that there's a few different things that it could mean, but the biggest one that customers are looking at are did my filters fail? Are my filters clogged? Do my filters collapse? All of that fun stuff. So that's where the customer was nervous, and we came and we started looking at it. But because we were capturing the whole startup, we really didn't have to guess about it. We could just watch it, and the data showed up, and yeah, the DP started super high, and then over that first 5-10 minutes, as everything warms up and we start getting a load pulled from our equipment, uh, everything starts to smooth out and settles out exactly where it should be. So instead of a nervous phone call, the customer gets a report. We did the analysis. Here's your startup data. Your system came up exactly the way it was supposed to. Everything looks good. And here's the bonus. Now that startup is on file. So the next time we service that equipment, we can capture another startup, and I have something to compare against. So even for customers that don't have that historical data on their equipment, we're kind of building it for them for that that hour at a time of startup data. And there's a huge value in that because we're creating historical data. And with that historical data, you can do so much. You can really, just from seeing how things react differently from month to month, uh, you can start to paint that picture. It's not as clear of a picture as if you're doing that continuous data, but you're still painting a picture. And again, it's cool. It's a cool picture because now you kind of have this knowledge of, yep, that's the way that this thing starts up. That's the way that it should be. So when you see something happening that's not what you're used to, you can flag that pretty quickly. So I feel like I've spent a lot of times talking about how, hey, look, this is so great. Data collection is great. And you know, again, I'm a little biased because I think it's a really fascinating subject. Just because, again, even throughout my career with working in the different industries, how different the data is that's important changed so rapidly. But there's been one thing that I see constantly, and eh, it's not funny, but it's kind of one of those things that you see it way more often than you'd want to, and it's dead data. So, dead data is when you're collecting the data and nothing happens with it; it just sits there. And I'd almost argue that dead data is just as bad as no data, because the problem with the dead data is you've paid the cost of collecting it and you've gotten none of the value out of it. And you see a lot of this on the paper end of the spectrum. And kind of here's what it looks like. The operators are doing their job. They're every hour they walk the floor, they take their readings, they fill out their forms, they hand them in at the end of every shift, day after day, shift after shift, exactly like they're supposed to. And then those forms go into a binder. And nobody ever looks at that binder again until something fails. And then the failure happens, and suddenly everybody's trying to do a root cause analysis, and they're frantically flipping through that binder going, wait, was this trending up? Did we have temperature start climbing? What does this data tell us? And a lot of times the answer is it's visible. It's right there. It it was right there on the forms in somebody's handwriting for weeks. The data caught the failure coming. The system around the data just wasn't really built to do anything about it till after the fact. And again, I want to be clear, it's not the operator's fault. They did their jobs exactly the way they're supposed to. The problem is the medium. Paper data is really reactive by nature. You can't trend it real time. You can't put an alarm on it. It really only ever becomes useful as a post mortem. And I think that that's why, yeah, I love doing the reports on the continuous monitoring of data, because every single thing that gets flagged in analysis gets flagged with an action item. So here's what we found, here's what it means, and here's what needs to be done about it. Because a finding with no action item is just a fancier version of the binder. The point was never to generate just a nice looking document. The point is to actually use the data to inform decisions, because the value of your data isn't really determined by how much you collect. It's the value is really determined by whether you actually do something with that data before it forces you to do something with it. So here's where I land on all this. The spectrum that we started with, the clipboards to PLCs to the full blown data collection historians. I used to think of it as a technology spectrum. Who has the fancy stuff and who doesn't. But I don't really think of it like that anymore. It's a spectrum of what's possible. The paper gets you to a postmortem. PLC data gets you some real time visibility. The full historian gets you trending, prediction, baselines. And the ability to find a valve creeping open over 10 minutes or a bearing failing over 8 runs or proof that a startup went exactly the way it should. But, none of it, not not even one level on that spectrum does anything on its own because even the best SCADA system in the world goes dead the moment that nobody's looking at it. A historian full of data that no one analyzes is just a way, way more expensive binder. Collecting the data is step one. Somebody actually paying attention to that data, you know, that's the true value in it. And honestly, that's been one of the most satisfying parts of all this data that I've been working with this year. It's not the collection. The collection's boring. It really is. You set up some code that pulls the PLC, pulls the data, and that's about it. The real cool part for me, and the part that I really enjoy, is pulling that data and finding the story that's hiding in it. Being able to talk to a customer and say, this is what your equipment's been telling you. This is From the Bucket, where controls design meets reality. Until next time.